we have seen now that integral of a product of a power function with an exponential or a trigonometric function can usually be evaluated using integration by parts. Another telltale sign that integration by parts will succeed is integral of an inverse function, such as logarithm, as we have here now, or integral of one of the inverse trig functions, and so on. In general, if you have integral of an inverse function, it's a good sign that integration by parts may be useful. To apply integration by parts here, we need to divide our expression, as usual, into u and dv. Now, you may say, but there is nothing to divide. There is just one factor, log x. So, indeed, this makes our life easier, since dv term must contain the differential. We know automatically that this here is the dv component, and the rest is u. In this expression, we are forced to choose dx as our dv because it is the component that contains differential, and we are forced effectively to set u to be equal to log x. So there is complete rigidity here in the choice of u and dv. Now, with that in mind, let's see what we have. So the setup is that we have u equal to log x and dv equal to dx, which means that v is x itself, the antiderivative of 1, and du is the derivative of log times dx. So that's dx divided by x. Great. The right-hand side of the integration by parts formula has u times v, so that's log x times x, minus integral of v du, which here becomes integral of x times 1 over x dx. And remarkably, in this case, these two terms cancel out, and we end up with log x times x minus integral of 1 dx, which is nothing but x log x minus x plus a constant, since antiderivative of 1 is x, and then we just add a constant to capture all the possible antiderivatives. And so as a result, the integral of log x dx is x log x minus x plus a constant. As you can easily verify by taking derivative this expression, you should obtain log of x. Let us look at another example where we will again deal with antiderivative with an integral of an inverse function, but now, for a change, we will apply integration by parts rule to a definite integral. In other words, an integral that has limits of integration. So we will calculate the integral from 0 to 1 of the inverse tangent of x. So here we have the inverse tangent of x dx, integrated from 0 to 1. Now, in this case, it will be useful to apply integration by parts formula in its original form. If you remember, we first obtained the formula of integration by parts as f of x times g prime of x dx equals f of x times g of x minus integral of g of x f prime of x dx. And so here, in this form, where we haven't applied the substitution for u and v yet, will be the more suitable one for definite integrals like this. So what we have to do in order to compute a definite integral is, since this line gives us the antiderivative of fx times g prime of x, this being the antiderivative, if we use the fundamental theorem of calculus and take the difference of two values of the antiderivative at a and at b, we obtain the definite integral. Right? So what I'm using here is that fundamental theorem of calculus tells me integral from a to b of x, some other f. This actually doesn't have to be the same f. But this is the f from fundamental theorem of calculus. The definite integral is equal to difference of values of the antiderivative. Using that, I'm going to take this line, which gives me the expression for the antiderivative, and take its difference at the value a and at the value b. The same here. I will take this product and evaluate it at b, then subtract its value at a, and the same here. So I took the entire line, I evaluated at point b, then subtracted its value at point a. So this difference gives me this modified expression here. Perfect. And now this shows me how to apply integration by parts for definite integrals, which is what I have here. Great. Now on to how we're going to choose these parts. Because you can still think of them as u and v. We just need to know that eventually we'll take the difference between 0 and 1, like so. But you can still think of them as u and v. So again, in the same way as before, I see that I must take this expression to be my u, and I must take this expression to be my dv. There's no freedom here. That's all I can do. So my u is inverse tangent of x, dv is dx, which means that v must be x, and du is the derivative of inverse tangent times dx. So the derivative of inverse tangent gives me 1 over 1 plus x squared times dx gives me this, and I shall rewrite this integral now as u times v, so that's x times the inverse tangent x, minus integral of v du. That would be v times du, which is 1 over 1 plus x squared dx. And remember, since I'm using this formula for integration by parts over here, I must also take the difference between the values of all the expressions involved at my a and b, which are 0 and 1. So what I will do is I will plug in x equals 0 and x equals 1, like so. Now this is the transformed expression for the original definite integral. What do I do with this now? Well, the first expression over here is just a difference. I can evaluate these two functions at 1, evaluate them at 0, take the difference. That's it. So that gives me 1 times inverse tangent of 1. Inverse tangent of 1 is pi over 4 minus 0 times inverse tangent of 0. Inverse tangent of 0 is also 0, incidentally, but whatever it is, it already is multiplied by 0. So this difference here comes up to pi over 2. And then minus this new integral that I'm now supposed to evaluate. How shall I evaluate this integral? So there's nothing that could cause us to believe that this requires another integration by parts. Instead, we'll use the only other tool from our toolbox. We will apply U substitution here. So let me take this integral and evaluate it separately over here. I shall have integral from 0 to 1 x over 1 plus x squared dx. What I shall do is apply a U sub to it. So I will use U again. This U is not to be confused with the previous U. This U comes from the U sub. The previous U came from integration by parts. I will set U to be the denominator, 1 plus x squared. So that then du is 2x times dx, the derivative of u times dx. Which results in a new integral. Note that previously I have x times dx in the numerator, which is 1/2 of du in terms of my new variable. 1/2 of du is precisely x dx. So I have 1/2 of du in the numerator divided by u. So this is what I have to evaluate, the integral I have to evaluate in terms of u. Now, the range of integration now changes. So my x variable changed between 0 and 1, which means that my u variable will change between whatever values it takes for these respective x's. So when x is 0 at the lower bound of integration, u is equal to 1 plus 0 squared, which is 1. When x is 1 at the upper bound of integration, u is equal to 1 plus 1 squared, so that would be 2. Result, this is what I'm integrating presently. Great. We take 1/2 outside the integral. I'm left with integral from 1 to 2 du over u, which has a straightforward antiderivative. So I need the antiderivative to 1 over u, which, as you should recall, is log of absolute value of u, and I will take the difference of this log from 1 to 2, which gives me log 2 over 2. Indeed, if I evaluate log at 2, I just get log 2. Log of 1 gives me 0. I will have log of 2 divided by 2 because of this 1/2. And this here gives me the value of the integral I obtained after using integration by parts. And then I'm ready to write down the answer. I have pi over 2 that comes from this difference here minus log 2 over 2, which is the final answer for this question. Since we started with a definite integral, the answer is a number. So when computing a definite integral, because I made a change of variables in the definite integral and I changed the limits of integration, I do not need to reverse this substitution. Once I arrive at a number, this is it. The value of this definite integral is log 2 over 2. It is a number. It does not require the inverse change of variables, just a value. And then once I substitute that value into my difference over here, I obtain the answer to example 4. And so as a result, we just saw how to apply integration over parts to definite integrals. Basically, all you have to do is to take the difference of your right-hand side you obtain after integration by parts between the two limits of integration that you have on the left. So we can write this formally now, that if you want to integrate from a to b some expression equal to u times dv, all you have to do is to take u times v, evaluate its difference at a, b, and subtract the definite integral from a to b v du. So you should be aware that a and b refer to the independent variable here. So a and b are the values taken by x. U and v are both functions of x. Implicit form of these functions can be seen from this line in green over here. So that is how you use integration by parts for definite integrals.